Gentlemen, I'm in the garden. That means that today we're going to have a pretty serious video. And I've been looking forward to doing this for a while now. If you haven't already seen Derek's recent video on Wilson Audio Lab's channel where he dynos the Audiopipe 3K full bridge Brazilian style amplifier, then go check it out because this is a follow-up video of that where we do a little collaboration. In that video, Derek got me to do a little segment for his video where I explained a little bit about full bridge, what it is, and I talked about the circuit design and the guts in this Audiopipe amplifier. Now in doing so, I discovered that this amplifier is actually a direct clone of the Taramps HD3000. However, the strange thing is that the Taramps HD3000 on Derek's dyno makes rated power. However, despite being an exact copy of that amplifier, the Audiopipe fails to make its rated power by quite a considerable margin, about 800 watts to 1000 watts less than the Taramps, even though it's exactly the same inside. So the idea of today's video, these amplifiers have come all the way from the States, all the way from Derek's workshop to me in the UK, and the idea of today is to take these amplifiers apart, look at the differences and what corners were obviously cut in the production of the Audiopipe, see why it loses 800 to 1000 watts over the Taramps, fix those problems. We're going to modify this amplifier to force it to do its rated power, find out what the issues are and rectify them, and then send it back to Derek in the States for him to make a new video where he dynos the newly modified Audiopipe amplifier to see how much power I have managed to squeeze out of it. So follow me into the workshop. We're going to dive deep into these two amplifiers, find out every little difference between them, and then fix any issues that we find with the Audiopipe that's preventing it from making the same power as its grandfather, the Taramps HD3000. Okay, firstly then, let's crack these things open and have a look inside. I already compared the internals of these on Derek's video, so if you haven't seen that, go check it out. But as we can see here, identical circuits in every way, so these should technically perform the same. I actually prefer the way the transformer is seated down on the Audiopipe compared to the Taramps, although the wind spacing is more even on the Taramps. You'll see other slight differences in the brands of caps and components used, but functionally they're the same. Now, the real interesting part, let's power them up and compare waves and voltages inside. Here are the power supply switching waves for both amplifiers, reading the MOSFET drain before the transformer. You can see a difference here in how the two amps run through their health check mode and increase the dead time, meaning that although both amps are using the same PIC chip, they've been programmed slightly differently. This is also the case with the LED sequence during power up on the front. Small difference, but it shows that the factory in China have not extracted and dumped the Brazilian firmware, instead rewritten it themselves for this PIC with some slight variance. The two amps have identical switch waves, bang on 25 kHz and 21.5 volts RMS. This shape will then be mimicked on the secondary wind of the transformer, but at a higher voltage. This is where things get weird. The Audiopipe's transformer is stepping the voltage up to a 65.5 volt RMS wave, whereas the Taramps steps it up to 80.5 volts RMS. What? So already, since the sole factor that defines output power is rail voltage, we have found the reason the Audiopipe does not make its rated power. When cloning this amplifier, it seems that the factory in China have made an error or something with the number of turns on the secondary wind or the primary wind, which the ratio between them will define the output voltage on the secondary wind. To be honest, this is not what I expected at all. This is a legitimate design error rather than a lack of power due to cheaper manufacturing processes or materials. It doesn't explain the huge drop in efficiency at 1 ohm on the Audiopipe though, but we'll look into that a little bit later. Output power is tied directly to the voltage of the sine wave coming out the speaker terminals, which is limited by the rail voltages. Higher rails equals higher output power, provided the amp can pass the required current for that power. This is also why amps make more power when you feed them with a higher input voltage, seeing as the rail voltage is directly tied to the amount of voltage going in at the power terminals. I was fully expecting these amplifiers to be electrically identical and the difference in power down to thin PCB traces causing higher resistance along the main current path. However, that's not the case here. Let's continue on and see how this voltage difference changes the rest of the amplifier's operation. The rectified DC rail voltage of the Audiopipe ends up at 87 volts, whereas the Taramps cruises with 107 volts. If we completely ignore rail load droop and losses and plug these values in for a sine wave, the Audiopipe's 87 volt peak to peak sine wave is 30.7 volt RMS, which into a 1 ohm load in full bridge operation would produce 3770 watts RMS. However, the Taramps' 107 volt peak to peak sine wave is 37.8 volts, which in full bridge would produce a whopping 5700 watts RMS. That is a whole 2 kilowatts difference. Remember, these numbers are hypothetical, assuming that the rails don't drop under load, which they do quite a lot. And this is calculated at 14 volts of input, whereas these amps are rated for 3K at 12.6 volts. This highlights what a complete balls up that low rail voltage in the Audiopipe really is. Probing the low side output MOSFET drain reveals that the Class D switch frequency of both these amps is 182 kHz, which is horribly low for an amp claiming to be full range. For comparison, this Hertz HP1D sub-amp, designed only for low frequencies, runs at over 300 kHz, and most of these Class D 4-channel amps from the likes of B2, Sundown, DD, etc. are up at around 550 kHz. The next important thing we want to look at is the ability for the amplifier traces to pass current and see if one of these amps has thinner, higher resistance traces to the other one. To do this, I'm going to switch from my 14 volt bench supply to my high current 12 volt supply and hook up a 1 ohm load and run them at the exact same power level with a 10.1 volt RMS wave into the loads. When the tone is played, the Audiopipe's rail voltage drops from 71.5 volts to 65.3 volts. The Taramps in the same scenario drops from 89.7 volts to 83.8 volts. Due to the rail voltage differences here, it's hard to see which amp has the lower current path resistance. So let's take the number of volts dropped from each amp, 6.2 volts dropped for the Audiopipe and 5.9 volts dropped for the Taramps. This shows that the Audiopipe's rails dropped by 8.67% and the Taramps' rails dropped by 6.57%. So probably, as expected, the Taramps performed better in this scenario, and it has been built with less resistance across its components and traces, although the difference is not as vast as I initially thought, and the drop in output power as a result of the higher resistance on the Audiopipe will be minimal. Its main issue is still its low rail voltage. As a quick side note, look at the horrendous way these amps clip when under load. Ugh! Both are exactly the same, but it's easier to see the wave shape on the Audiopipe as for some reason its output is less noisy. The reason for this shape wave is down to how these amps work in only using one single positive rail voltage. Unlike conventional amplifiers, which have positive and negative rail voltages with the audio wave swinging to these points from ground, these use a single positive rail and the audio wave swings from a generated midpoint down to ground and up to the rail limit. When you push the sine wave to beyond this rail limit into clip, it gets capped off and would usually become flat at the top as it rides the rail before following the sine wave back down. But since we are driving a load during this time where the output becomes DC on the rail limit, the strain and current draw from this causes the rail voltage to drop or sag dramatically as high current is drawn, so the top of the wave becomes this saggy DC rail before finally falling with the signal and relieving the stress on the amp. This doesn't occur at the bottom of the wave due to the limit simply being ground rather than a generated rail voltage. Instead, the stress of being a flat line drags the rail voltage down again at the top. This happens to varying extents even when the amp is not in clip, as seen here by how the rail voltage fluctuates with the output sine wave at double the frequency of the sine wave. So it's producing a dip here when the sine wave is at its peak, and it's rising again back up to its top in between the sine wave peaks. In order to prevent this happening, you need more rail capacitors to store and supply energy, which smooths out this current-induced ripple. Alright, so I hope you are following so far. To summarize, we have found the culprit behind the lack of output power in the Audiopipe, that being a lack of voltage coming from the transformer secondary wind, resulting in a low rail voltage. And we've explored some of the characteristic differences between these amplifiers despite them being the exact same circuit design. Now it's time to take the Audiopipe, pull it apart, rectify that lack of rail voltage, do some work on the transformer, and then start looking into some additional modifications we can make to the amplifier to squeeze as much power out of it as we can before it goes back to Derek on the dyno. Now, although we already confirmed there didn't seem to be a drastic lack of trace thickness in the Audiopipe, I wanted to see if there was a difference in weight between these boards anyway, as it may reveal more about the build quality. Surprisingly, both were within 20 grams of each other, which is very close and maybe as a result of the difference in terminals or the amount of solder used throughout. Here is 20 grams of 4060 leaded solder for a reference. Okay, I have removed the transformer from the Audiopipe, which has allowed me to accurately count the number of turns on the primary and secondary. It's very easy to count the winds on the Taramps without removing the transformer because it has better color coding. You can easily kind of see which is which and count the turns on that one. So on both amplifiers we have 2 turns only on each primary. On the secondary wind the Taramps has 14 turns, however the Audiopipe only has 12 turns, thus resulting in our lower rail voltage issue and lack of output power. At this point, I have a few different options for how we progress forward with this. Number 1, the Janky solution. We could solder some additional wire onto the original secondary wind to make up for the lack of length, raise the rail voltage, and therefore raise our power output. It's really janky, but it should work. Number 2, the certified solution. Discard the original secondary wind and rewind it using a longer cable to give us the original 14 turns as intended. This is the exact same result as number 1, the janky solution, but just with more steps involved and a bit nicer. Number 3, the modders solution. Discard the original transformer winds completely and rewind using a lit wire to minimize the skin effect and also to increase current flow through the transformer. Moreover, we will add a couple more turns perhaps to the secondary wind to boost our rail voltage even further and thus increase power output even further, but within the limits of the original components on the output section like MOSFETs and capacitors. Number 4, the Overkill solution. Use an entirely different larger transformer, wind it up using lit wire much thicker than original, and whack on a whole bunch more turns on the secondary wind to boost the rail voltage way past the limits of the factory components in the output section, replace those for higher voltage to do insane amounts of power more than this amplifier was ever designed to. I already know what you want to see done, and of course it's the most powerful solution, isn't it? So here we have a spare donor board from a Banda Viking 7K, which makes around 9,000 watts at 14 volts 1 ohm. This is never going to see power again, it's busted, so I'm going to steal the transformer and remove all the original wire, leaving us with only the core. As you can see, this is a fair bit larger than the core from the original transformer. Nah, I'm not going to pretend I know a great deal about transformer design because honestly this is a weak area for me and it's something that I'd love to improve on. I do not come from an electronics background whatsoever. I've taken no courses, done any classes or anything like that. All of my experience has been gained from repairing car amplifiers that you have seen over the years on my YouTube channel. So, to offer some insight and experience into transformer design and more, I would like to introduce my man Anthony Volkman, mad scientist and amplifier expert from Missouri, USA, and he's going to answer some questions I have about getting the most from my transformer arrangements here. So we have my main man here on the video call, Anthony Volkman. What's up, my man? How's it going from halfway across the world?
Well, pretty good. What about you?
Yeah, man, absolutely roasting here today. A couple of questions to you then, my friend, if that's alright, is what would you do? Would you keep the original transformer and rewind it better to do more power, or would you take the larger core from the Banda transformer and wind that up and maybe have to move around some components on here to get it to fit, as you can see, but we're looking for probably like a decent jump in power, you know, not like 3,500 watts. I'm looking for, you know, kind of like a, whoa, how much power is that doing? Like kind of, you know, at least like a K, 1,500 watts more. So do you reckon the bigger transformer would be the one to go for here?
Yeah, actually I would, because it should be able to handle the extra power. You would like to add another 1,500 watts on top of the original actual 3,000 watts. Is that correct?
Yeah, we were like at least another 1,000 watts. Basically, because I had this larger transformer core sitting around, I was hoping that to be a kind of like extra headroom. Let's throw this in here, and then well, at least we're not going to be bottlenecked by the transformer. My bottleneck will probably be things like output inductor or the FET or something else. I don't want my transformer to be a limiting factor here. So
since that bigger core came out of the band at Full Bridge, I already would be pretty sure, almost positive, that it would be able to handle the extra current draw from it, because that core is already designed for the larger magnetic flow to flex. It's going to be very powerful. Now, that smaller one that you have, it may actually not even be an authentic high-quality core, because it's a Chinese knockoff of the Taramps. I would definitely install that bigger core. Definitely install these.
Okay.
Definitely, if it doesn't have Zener diodes across the gates of the MOSFET, I would install it.
Yeah,
Make sure
at the moment, neither amps have Zener diodes across the gate. So, yeah, okay, awesome. Yeah, I'll be looking to... Yeah, no, really, there's just literally... Okay, awesome. So, we have come to the conclusion then that the larger core is the one to go for, with some drive circuit modifications to the original circuit. So, my next question to you is going to be regarding the wire that I'm going to use to rewind this core with. Now, I've read up a little bit about something called the skin effect, where if you're using too higher gauge wire, copper wire on the transformer, then the current will travel around the edge, around the outer diameter of the wire, rather than through it completely as you increase the frequency. So as I'm wanting to run this at a higher frequency than stock due to higher power demands, I want to make sure that we get as much power through this as possible. So would you recommend that I use thicker cabling and lots of it on this larger core, or would you suggest that if we're going for a higher frequency, I use a crap load of thinner strand wire, like a whole crap load of it, so that it's still very thick but each strand is thin? What do you reckon about that?
That is an extremely good question. So instead of the magnetic field combining or pressing whatever inside that wire, the magnetic field actually pushes the electrons to the surface of the wire, because electrons have electrical and magnetic moments, which means they're little tiny magnets. So as you push voltage through it, they align, which means they turn into a magnet. Well, as you push voltage through, for every action, there's an equal and opposite reaction. So they actually push back, which is why you get eddy currents, which is to drop a magnet through a copper tube, slow it down. That's eddy current. Here's what you do. Litz wire is a specific type of wire that I use in superconducting magnetic structures for like fusion reactors or things like that. If I'm not using YBCO, you can look that up on your own. Yttrium barium superoxide. So what that is you use stranded wire. And I cheat. I actually use like 36 gauge wire. And just like you said, you build up enough of these in parallel where they make a thick wire. And then you take a bunch of those and run them in parallel and wide the secondary and your primary of your toroidal core transformer. That alone will actually cause you to have an insane amount of power capability, because it will actually be able to handle the current, and it will also be able to generate a magnetic field without causing the skin effect at one cost, because current draw will be greater, because the wire will not be limiting the current as much. Solely the XL, or the inductive reactance of the core itself, will be. So this is Litz wire. We have many strands of thin wire wrapped together. As you can tell, it looks wrapped very tightly, and that's because it is. Now, the secondary is actually outputting voltage at 50,000 times a second. The skin effect takes effect very heavily once you start crossing that frequency border.
Okay.
So once you start increasing the frequency, I do believe it would be a good idea to use this wire. And in my opinion, I believe it's a very good benefit to use this wire.
Awesome.
Even if you did not increase the frequency.
Okay, got you. This looks crazy. So, guys, this looks like your regular kind of copper wire that you might find in a piece of 8 gauge wire or something. But what we're actually looking at there, those strands, those tiny thin strands, are actually laminated, aren't they? They're isolated. They're electrically insulated from one another. Correct?
That's correct.
Wow.
It has to be isolated. Otherwise, it turns it into one big
It turns it
conductor.
into a big coil anyway, yeah. Damn, that's crazy. Okay, I can see how that could be time consuming to make yourself. But yeah, you can buy this stuff, right? So maybe if this isn't too expensive and I don't need a crazy amount of length, really, to be honest, on this transformer, I'll probably just go ahead and buy some of this lit wire if you think its benefits will be worthy of this mod.
I do. I really do.
My next question, I guess, is going to be slightly related to the frequency as I'm sort of turning it up. So my initial thought with the frequency is once we've got our new transformer wound and installed is to run the amplifier with just the power supply section hooked up on a very small load across the secondary, just to kind of load it, just to get it, balanced or whatever. And then I would monitor the current draw from the amplifier from the, on my power supply, and start increasing the frequency and monitor the idle current draw. I'm assuming, my guess is that I'll get to a point where the current draw at idle suddenly starts to shoot up, and is that the point when my frequency is getting too high and I should back off a bit, or is it more in depth than that?
That is basically, that's absolutely correct, because then the inductive reactance is too low.
Yeah. So
it actually should get dead short.
Okay.
And the impedance drops off.
Perfect.
That's all we need to know about that. So you're absolutely correct about that. That is 100% correct. Yeah.
Listen, I really appreciate you taking the time out of your day here to just sort of talk a few things with me and to confirm my thoughts or my findings, and answer a few questions that I've got surrounding Transformers, which is, like I say, your insight has been invaluable in improving my understanding in Transformers, kind of fill that gap a little bit. I can now blag my way through Transformers a little bit better than I could before, so that's cool, and hopefully it should allow this modification to be successful, because like you say, I've only kind of got one shot at this. Once it goes back to Derek in the States, it's out of my hands. Like if it blows up on his bench, that's the whole kind of video ruined pretty much. But yeah, so awesome. No, thanks again, man, and we'll speak soon.
Okay. Peace out, man.
So yeah, like I said, that is the difference between someone that really knows their background in electronics compared to me like 4 or 5 years ago. I didn't even know what a MOSFET was. I didn't know the difference between a Zener diode and a flipping inductor. Like, I knew nothing about electronics. So to summarize then, from the call with Anthony, we have decided that for our transformer modification on the Audiopipe, we are going to be using the Banda Viking 7K transformer core, which is larger than the original core from the Audiopipe and the Taramps. That will give us headroom, and we're going to rewind this transformer core with similar primary using lit wire, and the secondary we're going to wind not just to the 14 winds that it should have been, that the Taramps is designed with. We're going to go beyond that into a higher voltage to give us higher rails, therefore higher output sine wave amplitude, which will result in more power being driven to the load on the outputs, whether it's the speaker or the dyno. And as a result of the higher voltage on the secondary winds, we are going to have to change up the rail capacitor here, and possibly the output MOSFETs, and possibly part of the voltage regulator. I need to just look into this real quick, because obviously if we're increasing the rail voltage, there might be other things that use the rail voltage and lower it down, regulate it for some of these small chips or drivers here. So if we go busting up the rail voltage super high, we might be overloading these regulator circuits and asking them to drop too much voltage. So the output inductor we're going to leave as standard for now, and we're going to see how it copes with the increased power. If it doesn't cope, then I will just confirm with Mr. Volkman what the best solution is. I think he was saying to just make this bigger, this output inductor bigger, but keep the inductance roughly the same, or maybe increase it slightly so that it's more dampened. But yeah, exciting stuff. I've learned a lot, and I hope you have too. Let's move on with the mods and wind this new transformer. Okay, that wraps it up for part 1. We found out why the Audiopipe was unable to make its rated power despite being a clear, obvious clone attempt of the HD3000, and we've discussed some of the modifications and the process that we're going to go by in getting this amplifier to not only make its rated power, but hopefully a whole lot more. So guys, subscribe for part 2, which is where we're going to get really technical. We're going to look into some crazy stuff like winding up the banded transformer core with the Litz wire to a high voltage, changing out the output MOSFETs, capacitors, and anything else in the output section that needs to be changed for the higher voltage. Then going to be looking at how we can modify the protection circuit so that we can tune it so that it protects the components in case the alternator accidentally chucks out 18 volts and the amplifier, we're going to make it go into protect at that point to save the components, just like it would have done originally. And we're also going to be looking at modifying the circuit for the power supply PWM generation to maximize the efficiency of our new transformer. It's a really in-depth mod and I'm really excited to show it to you. I've got a bunch of stuff recorded already, but I did hit some slight hurdles along the way, and also moving house and everything really got in the way, and so rather than just putting it out as one long video, I decided to split it up into 2 parts, so that at least now you've got something that you can watch and you can see why the Audiopipe struggled to make its rated power. And then stay tuned for part 2 that I'm currently working really hard on, which is going to be a really in-depth modification and some kind of crazy circuit design stuff to get this Audiopipe to make as much power as we can physically squeeze into that tiny compact size. So guys, thanks for watching. Any questions, give me a shout. There's a link in the description to Anthony Volkman's channel. Go check it out. He's an absolute madman, and yeah, his knowledge level in just general electronics, and especially with transformers, inductors, and amplifier modification is way above mine. So go check him out, and I will see you in the next video.